Imagine a telescope so sharp it rewinds the universe where the first galaxies blaze too bright, spectral lines go missing like withheld answers, and dust appears before the clocks allow. The James Webb Space Telescope peers past comfort into cosmic dawn, mapping cold veils wrapped around hot hearts, weighing invisible matter by the arcs it bends and catching newborn black holes outgrowing their tiny homes. Even alien skies misbehave with rock clouds, chemical storms and winds that race the night. This is not hype, this is the data, and it quietly shocks. The telescope holds steady against the dark and waits for the past to arrive as the first deep field blooms into view. On a mid-July day in the year 2022, a foreground cluster shapes space into a gentle lens, and the James Webb Space Telescope gathers the amplified glow with mirrors tuned to faintness. The near-infrared camera operates between about 1 and 5 micrometers, where light from the earlier systems now resides, after its long stretch through expanding space. Points that would have vanished into noise under older eyes stand up as distinct smudges, some no wider than a few hundred parsecs across, at their own distance some lensed into delicate arcs that braid the image with quiet geometry. The catalogue begins in cautious steps. Objects are sifted by colour because hydrogen in intergalactic space has chewed away their short wavelength light, leaving a sharp drop between adjacent filters known as a Lyman break. When a source vanishes in bluer bands but persists in redder ones, it becomes a candidate for extreme distance. Counts are tallied, uncertainties are stacked, spurious detections are removed, and the remainder is still larger than expected. The first surprise is statistical and soft-spoken. There are too many bright, tiny galaxies where time should have been too short for such confidence. Models had predicted that in the first few 100 million years, after the beginning matter would lie mostly in small dim clumps still learning to form stars. Yet the deep field returns a population whose brightness suggests vigorous star birth, and compact structures already able to hold themselves together. From colours alone one can estimate redshift, a measure of how much the universe has expanded since the light was emitted. Several candidates point to redshifts beyond 10, and a few press higher still. The brightness of these points implies a star formation rate that even with conservative assumptions runs into thousands of solar masses per year, for some lens sources once magnifications are accounted for. Sizes derived from the blurred footprints look small, yet their light is concentrated and strong, hinting at dense clusters of young stars and perhaps the earliest dust beginning to veil them. Every ingredient in the inference chain is checked. The light from cool stars in the foreground could masquerade as young galaxies, but their spectral slopes and shapes do not match. Emission from line features could inflate flux in a single filter and mimic a steep colour break, but the patterns appear across multiple bands. The mass model of the lensing cluster could be wrong, leading to magnification errors, yet independent reconstructions that follow the gentle distortions of many background arcs converge on similar values. Each test removes an easy escape from the conclusion, leaving a shape of truth that grows clearer by subtraction. Spectrographs then enter turning colours into fingerprints. The near-infrared spectrograph isolates emission lines whose rest frame wavelengths are known and whose red-shifted positions fix distance with precision. For a subset of the brightest candidates, a hydrogen line steps into view exactly where predicted by the photometric estimates, and distances are nailed down to within small margins. Redshifts near 12 are not rare in the confirmations, and a couple of sources climb beyond that. The times involved shrink to numbers that fit within the first few 100 million years. Within that narrow window, stars must have formed, burned, and in some cases died to enrich their surroundings, seeding the raw material for later complexity. The galaxy luminosity function a curve that counts how many galaxies exist. At each brightness bends upward more than anticipated at the luminous end. This is not a single discordant point but an ensemble. It is a quiet tilt that moves theory away from comfort. The early universe appears more efficient at making bright things than many models had prepared for. Explanations unfurl in careful ranks. Star formation could be more bursty than assumed, spiking into brief intense episodes that make small systems appear outsized when caught at the right moment. Stellar populations could be skewed toward more massive stars which shine fiercely and die young, lifting brightness per unit mass, while also enriching their surroundings quickly. Feedback from newborn stars, which normally stirs and heats the gas strongly enough to slow further growth, might couple differently to the earliest gas, allowing denser collapse to proceed. Dark matter, which sets the scaffolding on which galaxies assemble, might cluster more efficiently on small scales than standard assumptions allow, providing deeper wells sooner. Each speculative path walks carefully beside the data, never racing ahead, yet each is encouraged by how the evidence holds across independent fields. The lens is both gift and challenge. Magnification turns the inaccessible into the measurable, but it also demands detailed accounting. The foreground cluster is modelled by matching the curvature and separation of multiple arcs, by mapping where faint images appear in mirror symmetry, and by comparing mass inferred from gravitational tug with mass implied by the light of cluster galaxies and their hot gas. Correcting for magnification still leaves background sources that remain strikingly bright for their tender ages. The field of view not shaped by the lens tells a similar story with fewer extremes. Bright compact galaxies appear there too, simply fewer in number as expected without the extra boost. The mid-infrared instrument begins to whisper about dust. At wavelengths between about 7 and 15 micrometers, warm grains glow in a few sources that are older but still ancient. Dust requires heavy elements, and heavy elements require earlier generations of stars to have lived and died. If dust is present so soon, then stellar furnaces have already run and exploded to fill their neighborhoods with carbon, oxygen, and silicon. Chemistry arrives on schedule only if the schedule was always tighter than expected. What begins as an image becomes a shift in chronology. The first deep view does not overturn cosmology. It trims the margins where growth had been slowed by assumption. It does not claim monsters where there should be mice. It shows many small predators that grew lean and quick in a young ecosystem. The shock is quiet because it is written in steady measurements and cross-checks in carefully corrected magnifications in spectra where lines appear exactly where distant physics says they should. With this opening look, the telescope reframes first light as a season rather than a single dawn, a span where structure and brightness gather faster than models had preferred. The map forward becomes obvious and demanding at once, longer exposures, wider fields, and serial confirmations that test whether early abundance survives sharper scrutiny. In the space between what is counted and what is explained, the intrigue rises without raising its voice. Time narrows as measurement replaces inference, and the early candidates accept or reject their place near the beginning. The near-infrared spectrograph takes center stage, carving light into precise lanes that mark how far it has been stretched by the expansion of space. When the hydrogen line born at a known wavelength arrives, displaced to far longer wavelengths, distance is fixed, and with it the cosmic age at emission. Confirmations stack near redshift 12 and beyond, placing starlight within the first few 100 million years after the origin. The arithmetic of the expanding universe is simple to state and hard to accept in the quiet of a control room where numbers carry weight. If a galaxy shines so soon, It implies reservoirs of gas that collapse, rapidly stars that ignite in crowded clusters, and cycles of birth and death that move at a pace some models had reserved for later epochs. The telescope watches more than once because any claim to outrun ordinary growth must survive repetition. A second stare with the near-infrared camera fixes shapes and sizes again, under slightly different roll angles, confirming that the compact cores are not artifacts of scattered light or stray rays through the optics. A third look with the mid-infrared instrument senses a faint warmth that suggests dust has already formed in a subset of the sources that are slightly older, yet still very ancient. The timing becomes the most unsettling element. It is not only that galaxies exist early, it is that some look mature relative to their youth. The spectral energy distributions, which are the curves describing how brightness changes with wavelength, show hints of breaks that in later times arise from populations of stars that have aged beyond their most massive phases. Interpreted carefully and compared across filters, these features suggest that even before the confirmed observation, prior bursts of star formation must have occurred to plant those signatures. The clock seems to have started almost as soon as darkness would have allowed. Hydrogen in the intergalactic medium remains largely neutral in the earliest moments, and that neutral hydrogen should block certain kinds of escaping light. Indeed, the signature hydrogen emission line appears weak or absent in many extreme sources, a sign that the surrounding cosmos has not yet been fully ionized. Yet the metal lines from oxygen and carbon shifted into the near-infrared and split by the spectrograph into narrow peaks, peek through in a few cases. Heavy elements only arise inside stars, which means at least one generation of stars has lived and died to enrich the gas. The presence of those lines at such early times compresses allowed histories into tight spirals of rapid formation, quick enrichment, and new bursts fueled by recycled material. Each parameter that could relieve the pressure of time is tested. Star formation efficiency could be higher in pristine gas where cooling occurs differently. The models are adjusted and produce some relief, but not enough to erase the bright tail of the observed population. The fraction of very massive stars could be larger at first. That change increases light for a given mass and accelerates enrichment, but it also injects powerful feedback that can drive gas away. Feedback strength is tuned and compared against observed sizes and inferred gas densities. The emerging picture does not collapse, but it resists any single easy adjustment. The contribution of gravitational lensing is scrutinized next. For the most extreme redshift conformations, magnification from a foreground cluster could have turned ordinary systems into apparently prodigious ones. The mass distribution of the lens is rebuilt by mapping multiple images of known background galaxies, by modeling the hot gas that suffuses the cluster, and by cross-checking with independent reconstructions. Magnifications shrink and grow within uncertainties, but the earlier sources remain early even when boosts are modest. The tension lives not only at the bright end. Number counts at intermediate luminosities also lean high, at redshifts near 10 and beyond. This means that the apparent early surge is not merely a selection of outliers, but a broader shift in abundance. The theoretical curve that tracks how quickly dark matter halos form and how baryons cool within them bends upward in response, and the change echoes into other expectations. If stars ignited earlier and more vigorously, then the timeline of reionization, the grand turning on of the cosmos, must reflect that activity. Phase by phase, the telescope maps the neutral fraction of hydrogen by looking for the disappearance or survival of certain spectral features across many sight lines. The data suggest a patchwork sky at those times with ionized bubbles around vigorous galaxies and neutral fog elsewhere. time thus stretches thin by becoming uneven, with pockets of acceleration interleaved with regions that lag. The earliest black holes add pressure to the schedule. Compact cores in a few galaxies radiate like engines too large for their host masses, implying central objects that have grown quickly. If those black holes exist by these times, then seeds must have formed either from direct collapse of dense gas or from the deaths of very massive stars almost immediately after the first stars arrived. Either path compresses the allowable sequence further because rapid accretion or direct collapse requires specific conditions that cannot wait. The telescope does not claim certainty about these seeds. It simply reports that some nuclei are too bright, too compact, and too energetic to be explained entirely by starlight. The alternative is to mismeasure distance, but the spectral lines argue against that, and the continuum shape agrees. Time remains the stubborn point. In the face of this compression, astrophysicists consider whether the cosmic expansion history could be tuned within observational limits to change inferred ages by a small amount. Most adjustments are strongly constrained by the cosmic microwave background and by large-scale structure. A small shift does not solve the early brightness without creating larger conflicts elsewhere. The answer returns to process rather than to parameters. Perhaps the earliest gas cools through channels that later disappear. Perhaps the geometry of gas flows into halos is more filamentary and direct than expected, allowing cold streams to feed young galaxies without being heated into delay. Observations of nearby analogues dwarf galaxies with low metallicity, and intense star formation guide expectations. The telescope meanwhile continues to measure. Exposure time deepens, signal-to-noise rises, and error bars shrink. What remains after those refinements is a cadre of galaxies that look confidently placed within a few 100 million years of the beginning, and that carry signs of internal history. They are not impossibly massive, rather they are surprisingly organized and bright. The shock lies not in a violation but in a rearrangement of pace. Growth does not creep, it sprints in sprints, slows and sprints again. The universe appears to have used its first steps to run. Brightness becomes the fulcrum on which expectations tilt. The telescope gathers near-infrared light that has travelled for most of cosmic time and finds compact sources whose luminosities rival systems many times larger at later epochs. The near-infrared camera measures flux through adjacent filters, and from those fluxes astronomers estimate how many new stars would be required to produce the observed glow. The implied rates are ambitious even after careful accounting for gravitational magnification, where a foreground cluster bends and boosts the light. When sizes are fitted by convolving point spread functions with small disks or clumps, the radii shrink to a few hundred parsecs at most, and sometimes to well under that. The surface brightness, which is light per area, rises to values that are hard to square, with mild continuous growth. To make that much light in that smaller volume, stars must be forming in bursts. The physics of such bursts is familiar from local starburst, but surprising so close to the beginning. Rapid inflow of cold gas along filaments can deliver fuel directly into a compact core. Once density crosses a threshold, cooling accelerates, fragmentation proceeds, and many clusters ignite nearly together. Starlight and supernovae then push back, stirring turbulence and heating the medium, which interrupts further collapse. The result is a duty cycle where the system alternates between blazing and quiescent phases. The telescope appears to have caught many galaxies in the blazing state. That could be chance, yet repeated fields and longer exposures continue to favour bright compact objects. Bursts also leave fingerprints beyond the raw light. Nebular emission lines from ionized hydrogen and oxygen, red-shifted into the near-infrared and mid-infrared bands, can add extra flux to broadband filters, When those lines fall inside a filter, photometry becomes inflated unless spectra are used to separate line and continuum. Teams account for this by modelling line contributions and by obtaining spectroscopy for representative samples. Even after subtracting likely line boosts, many sources remain brighter than conservative models predict for their age. Dust, which usually dims light, could complicate matters further. Early dust signatures appear in some older but still ancient galaxies, yet the youngest extreme candidates often seem relatively transparent, as if dust has not yet grown thick. That clarity means attenuation cannot be hiding large masses of unseen stars whose light is heavily absorbed. The brightness is genuine, not an artifact of dust that both reddens and conceals. Another possibility is that the mix of stellar masses skews toward heavier stars. At the beginning, a distribution sometimes called top-heavy, more massive stars shine much more per unit mass and live briefly, so a young population with a larger fraction of giants would look brighter for the same mass of gas turned into stars. This adjustment also accelerates the creation of heavy elements and dust consistent with the early hints of enrichment. Yet too many very massive stars would drive violent feedback which might disrupt the small galaxies entirely. The telescope tests this tension by examining sizes and by looking for outflow signatures in spectral lines. Where line profiles exist, some show modest broadening consistent with winds, but the compact morphologies persist, implying that feedback has not shattered the structures wholesale. Perhaps geometry matters flows, vent along low-density channels, while dense clumps keep forming stars. The size-to-luminosity relation sharpens the puzzle. In later times, brighter galaxies tend to be larger. In the early sample, many of the most luminous systems are tiny. This inversion forces a rethink of how quickly central densities can rise and how angular momentum is shed. Gas collapsing from large scales should retain spin that resists concentration, yet mergers and torques can drain that spin efficiently. The telescope offers hints of clumps and asymmetries that suggest such processes are at work even in youth. Gravitational lensing is both suspect and ally. Magnification can elevate ordinary sources into rare brightness bins, but careful reconstructions of lens mass anchored by multiple images and by independent methods constrain the boosts. After demagnifying, many galaxies still sit above the expectations of standard growth tracks. Lensing also stretches images, allowing finer structure to be resolved, and in those elongated views, small star-forming knots stand out like beads on a filament. These knots resemble the most intense superstar clusters known nearby, scaled into an epoch where the gas supply is richer and the cooling pathways more efficient. The role of cold streams becomes a central line of thought. In simulations, long thin rivers of gas feed galaxies through narrow pipes that avoid the heating typically imposed by shock fronts in massive halos. If the first halos are just large enough to attract such streams, but not large enough to create strong heating, then fuel arrives pre-cooled and ready to collapse. The telescope cannot see the streams directly, but the compactness and the sustained brightness argue that supply is not the limiting factor during bursts. This picture leads to a broader implication for the cosmic energy budget at early times. If many galaxies spend a significant fraction of their youth in burst mode, then the integrated background light should carry that signature. Measurements of faint background fluctuations in the near-infrared might then align with a sum of many compact bright episodes, rather than with a smooth gradual build. The telescope begins to touch this by mapping deep fields repeatedly and by measuring the subtle variation of faint light across the sky. Brightness also intersects with the growth of central black holes. In a few compact galaxies, a point-like core contributes disproportionately to the luminosity. The spectrum may carry high ionization lines or a power law-like shape that hints at accretion. If central objects are already active, they may both feed on and help regulate bursts by heating or expelling gas. The ratio of nuclear light to starlight becomes a diagnostic of how intertwined these engines are with star formation. Early indications show variety, with some nuclei quiet and others too loud for comfort. The telescope calibrates its expectations against nearby analogues. Blue compact dwarf galaxies with low metal content and extremely high specific rates of star formation present a partial echo of the distant systems, though they live in a markedly different environment. Their intense star-forming knots and strong nebular lines resemble what is seen when distance is scaled back and time is wound forward. This anchoring comparison increases confidence that the distant brightness is not an observational mirage. It is a physical state that galaxies can enter when gas is abundant and gravity is swift. Careful statistical treatment tempers enthusiasm with humility. Selection effects favor the detection of the most luminous objects near the sensitivity edge, and noise can push a few across thresholds of bias that must be corrected. Teams model these effects, insert artificial sources into real images, and recover them to measure completeness and bias. The corrected counts still show an excess of bright small galaxies at early times. This persistence is the quiet shock. The path forward is deliberate. Longer spectroscopy will separate line and continuum more cleanly. Deeper imaging will extend the size measurements to lower surface brightness. Outskirts testing whether some apparently tiny systems hide faint halos. Mid-infrared observations will search for embryonic dust and complex molecules that might already be present, tying brightness to chemical maturity. The brightness problem is not a single wall, but a set of doors, each opening to a slightly different room, where gas dynamics, stellar physics, and gravity conspire to produce more light than comfortable theories allowed. With each door opened, the sense grows that the early universe did not dawdle. It learned to burn bright quickly, and then to rest, and then to burn again. Structure rises out of youth with a composure that does not quite fit the age. The near-infrared camera, with resolution sharpened by long exposures and quiet optics, sketches faint outlines that look less like ragged clumps and more like organized forms. Some galaxies appear as elongated ovals with gentle brightness gradients, their light spreading along an axis, as if a disk has already settled. Others show knots strung along a faint spine, a chain that hints at matter flowing inward and lighting up in pockets where density crosses a trigger. In a few lensed cases, the foreground cluster stretches background shapes into arcs that also magnify them, unwrapping details that would otherwise be blurred. There, under favorable magnifications that are modeled carefully from multiple arc constraints, thin crescents resolve into structures with the central concentration and fainter outskirts, much like the precursors of rotating disks. The telescope does not stop at shape. The near-infrared spectrograph, equipped with an integral field unit that captures a small image and a spectrum at each point, turns faint glow into maps of motion. The positions of emission lines from hydrogen and from doubly ionized oxygen shift subtly across a galaxy's face. On one side, the line lands at a slightly shorter wavelength. On the other side, a slightly longer one, a signature of approaching and receding light, if interpreted as ordered rotation. The gradients are small because the systems are tiny, and the times are early, yet they align with the photometric major axes more often than chance would allow. Ordered motion in a place and era where turbulence should be the native language arrives as a measured whisper. Unease deepens because order takes time to assemble. To fashion a stable disk, gas must cool. settle and shed angular momentum in a way that balances gravity with rotation. In later epochs, bars and spiral arms redistribute momentum and feed central growth. Yet even in the early sample, there are hints of elongated central structures that could be the seeds of bars detected as inner isophotes with distinct angles, and as mild enhancements in stellar light aligned with kinematic axes. If those features are real, then internal dynamics have matured quickly enough to sculpt geometry not merely to collect matter. The chain galaxies amplify this theme. Their clumps are not randomly sown, but often spaced at distances that, when scaled by their own sizes, resemble the separation of giant star-forming complexes in later disks. If gravitational instability in a gas-rich sheet produces regular fragmentation, then clump spacing would follow a characteristic scale tied to surface density and rotation. The telescope cannot measure every parameter directly, but the observed spacing and relative brightness of knots match expectations of a heavy cool layer, prone to breaking into massive pieces that then migrate inward as they exchange angular momentum. Migration timescales are short in such compact systems, a few internal orbits at most, which means that even a small number of clumps could reshape the central concentration within the available cosmic time. Mergers also leave signatures, and they arrive at the scene in tandem with order rather than in its place. A fraction of galaxies show double nuclei asymmetries and tidal extensions that suggest recent encounters. Ordinarily, frequent mergers are invoked to explain disturbed irregular light. Here, however, some pairs and groups look on the verge of becoming single coherent systems. In lensed fields, the telescope catches mirror images of the same configuration, allowing a stereoscopic sense of shape that strengthens the case. Violent assembly and rapid settling appear less like consecutive chapters and more like alternating pages in the same notebook. Gravitational lensing acts as both magnifying glass and contour map for the mass distribution that bends light. When background galaxies are stretched around a cluster, the precise curvature and multiplicity of arcs encode the cluster's internal landscape, including the invisible matter that outweighs stars and gas. By fitting these patterns, observers generate mass maps with enough resolution to predict where additional counter-images should fall. When those are found, confidence in the model rises and the magnification of each background source is constrained within useful bounds. Correcting for this magnification reveals that even demagnified some galaxies remain remarkably thin, with axial ratios that suggest they are not spherical clumps, but flattened systems seen at various tilts. Thinness at early times implies cooling and coherence. It also hints at strong pressure support from rotation, rather than from random motion alone. The mid-infrared instrument adds a chemical layer to the geometry. In a subset of slightly older targets, emission from warm dust and from complex molecules appears with spatial offsets from the brightest young star clusters, as if feedback and winds have begun sculpting the interstellar medium into cavities and shells. Such structuring is the hallmark of regulated star formation in later galaxies, where energy from newborn stars clears space and sets the next round of collapse to occur along compressed edges. Seeing similar patterns scaled down and pushed back toward cosmic dawn suggests that self-regulation can start early in miniature form. The telescope weighs these inferences against every known trick of light. Point spread function mismatches can turn stars into false elongations, but stacks of stars across fields allow precise modelling of the instrumental shape. Detector artifacts could imprint spurious features, yet they do not repeat at the locations of interest within rotated and dithered data. Sky subtraction errors can carve artificial edges, but the structures persist across independent reductions. When the spectroscopic gradients are divided by the estimated diameter, a crude rotation speed emerges, Combining this with estimated mass from light and from dynamical modelling yields a ratio of rotation support to pressure support that lands closer to disk-like behaviour than to chaotic clumps. The uncertainties are real and large, yet the direction of the evidence is persistent. A thread of order runs through the cacophony. The presence of order so early does not refute the broader picture of hierarchical growth. Instead, it refines it with a message about timing and parallelism. Fragmentation, merger, and settling are not separated by long pauses. They overlap with efficiency that produces recognizable geometry, while the universe itself is still in its first few pages. If cold streams deliver fuel directly to small halos without significant heating, if turbulence decays quickly where density is high, and if angular momentum is redistributed by clump interactions and minor bars at pace, then thin rotating structures can appear rapidly, and then be stirred again by the next encounter. The telescope, by catching young systems in snapshots that sample this churn, builds a composite movie where serene frames and chaotic frames alternate. The shock is in realizing how many serene frames appear near the beginning. It is a calm that was not expected, a poise that suggests gravity works with a surer hand when gas is abundant and cooling is generous. From this new questions emerge that reach inward. If disks can settle early, how soon can spiral patterns organize? How soon can central black holes be fed by bars? How soon can stable planes of gas fuel the first complex molecules that precede life on future worlds? The path forward points to deeper velocity maps, longer exposures to chart faint outskirts, and joint campaigns with the Atacama Large Millimeter Array to trace cold gas that seeds and sustains these shapes. The James Webb Space Telescope does not declare answers. It lays down a geometry of clues, a lattice where order and youth hold together in surprising harmony, and invites theory to thread the spaces between them. Light unfolds into fingerprints, and something is not where it should be. The near-infrared spectrograph receives narrow beams sliced from tiny galaxies and spreads them into bands where each element leaves a recognizable mark. Hydrogen should speak loudly through the Lyman alpha emission line, a resonant shout that often blazes in youthful galaxies, but at the highest redshifts that shout is hushed. In many spectra, the hydrogen Lyman alpha line is muted or absent, even when the rest of the continuum is strong, and other clues insist that stars are forming quickly. The simplest explanation is that space between galaxies remains full of neutral hydrogen that scatters the line out of the line of sight. The suppression then becomes a map of the cosmic reionization process, the grand clearing of fog that follows the first waves of starlight. Yet the pattern is not uniform. In some sources, the Lyman alpha line survives as a faint red-shifted shoulder, displaced from where a symmetric profile would sit. That shift hints at winds moving gas toward and away from view, changing how photons escape. When the line appears, its asymmetry and displacement become a weather report for the interstellar medium inside a galaxy, and a climate report for the intergalactic medium outside it. The spectrograph does not stop at hydrogen. Doubly ionized oxygen, singly ionized oxygen, and the Balmer series of hydrogen in the rest frame optical range step into the near-infrared windows where the telescope is most sensitive. In several early galaxies, the ratio of oxygen lines to hydrogen lines lands at values that imply very high electron temperatures and low metal content conditions expected when gas is pristine and cooling is driven by a young and hard radiation field. But then a complication emerges. In a few cases, the oxygen line that should be paired closely with another is weaker than anticipated, and in others a line that should be present is barely there at all. The missing or muted lines could be the handiwork of density geometry or dust. If star-forming regions are compact and dense, collisional processes can silence certain transitions that would otherwise glow. If the gas is arranged in clumps pierced by clear channels, ionizing photons may escape without fully lighting the nebulae, causing the spectrum to undercount recombination light and to overcount harder continua. If dust grains of unusual composition grow quickly in the first supernova remnants, they can preferentially absorb or scatter lines with wavelengths that overlap specific resonances in molecules or solids. The instrument team checks the calibrations with obsessive care. Wavelength solutions are verified against skylines, and internal lamps' flat fields are corrected with independent exposures, and deep observations of standard stars confirm that subtle variations in sensitivity do not carve false troughs. Even after all of this cleaning, the absences persist. Absence itself becomes a number. When an expected line fails to rise above noise, the limit on its strength constrains the temperature, pressure, and ionization state of the gas. These limits then feed models that explore extreme star-forming environments. One family of solutions calls for an unusually high fraction of very hot, very massive stars whose spectra flood their surroundings with photon energies capable of stripping multiple electrons from oxygen and neon. In such a bath, the classic lower ionization lines weaken. Another path points to an escape of ionizing radiation into intergalactic space, which would reduce the recombination signatures within the galaxy and shift energy outward to affect the fog beyond. If true, these galaxies act as fissures through which the early universe vents light, hastening the end of the neutral era. Some spectra show a different kind of missing piece, the continuum dips, where a Balmer break might fall if an older population already lurks beneath the newer stars. The break is a step-like drop caused by absorption in the atmospheres of stars that are older than the most massive short-lived giants. When such a feature appears at these redshifts, it suggests that star formation has been running long enough to produce layers not just single flares, but in a subset of objects the expected complementary lines that would confirm this older population do not appear with the right balance. It is as if the light carries a memory of aging, but the gas refuses to echo it. The reconciliation could be that star formation occurs in bursts separated by brief calms, so that stellar light and nebular light are out of phase. Another hint lies in line widths and small velocity offsets between different species. Hydrogen lines sometimes arrive broader than oxygen lines, or vice versa, signaling multiple kinematic components that do not share the same motions. If dense star-forming clumps drive local outflows, while more quiescent gas orbits briskly in a nascent disk, then different lines will trace different layers, and a missing feature may simply belong to a layer not pierced by the chosen slit, or not bright enough at the moment of observation. Integral field mapping helps by covering small fields with spectral pixels, and a few targets reveal patchwork spectra where one knot flaunts strong oxygen while a neighbour suppresses it. Chemistry and dynamics thus intertwine to hide and reveal. A more radical possibility occupies a quiet corner of the discussion. If a fraction of stars are nearly metal-free, their radiation would be extremely hard, and certain lines might appear at strengths or ratios far from ordinary expectations, while others almost vanish. The spectrograph searches for telltale helium emission that would betray such populations, and in rare cases sees hints, but the evidence remains tentative. The danger of overinterpretation sits beside the excitement. Cosmic rays, shocks from nascent outflows, and young supernova remnants can mimic hard radiation fields. Microturbulence and unresolved temperature fluctuations can bias line ratio diagnostics. The team therefore triangulates by combining near-infrared spectroscopy with mid-infrared continuum measurements from the mid-infrared instrument and with submillimeter maps of cold gas from ground-based arrays. Where mid-infrared bands show aromatic features from complex hydrocarbons, chemistry has clearly advanced, making purely pristine populations less likely. Where submillimeter lines of carbon monoxide or ionized carbon appear, reservoirs and interfaces become visible, offering alternative sites for missing nebular light. The pattern across many targets still points to a mixed reality. Some early galaxies channel a significant portion of their hardest light into surrounding space. Some cradle star-forming islands so dense that classical lines are muffled. Some carry layered histories visible in continuum steps but hidden in gas tracers. The shock is not that a single line is missing, but that the absences are organized. They recur with redshift and with compactness. They correlate with signs of outflows and with tentative rotation. They strengthen where imaging suggests porous structure and ease where shapes look more cocooned. From these measured silences, astrophysicists extract boundary conditions for the first cycles of star formation. How quickly can grains grow in the ashes of the earliest explosions? How easily can young clusters open escape hatches? And how patchy was the end of cosmic fog? The James Webb Space Telescope answers by refusing to fill every line. In the spaces where light should be and is not a new map, appears one that guides the next deep stares and the next comparisons with theory. The universe hides with intention, and the spectrograph, by counting what is missing, reveals that intention with numbers rather than with noise. Dust appears where clocks say it should not, and the mid-infrared instrument becomes the sense that feels it. The telescope turns to wavelengths between roughly 7 and 15 micrometers, where warm grains glow, and where certain molecular vibrations add gentle ridges to the spectrum. In galaxies within the first billion years, faint rises appear at rest wavelengths near 3.36.27.78.6 and 11.3 micrometers, the places where carbon-rich aromatic molecules tend to sing. Each rise is small, yet the pattern repeats across sources whose distances are fixed by the near-infrared spectrograph. The implication is simple and quietly disruptive. Complex hydrocarbons and silicate grains have assembled while the universe is still very young. To grow such grains, heavy elements must already be present, and heavy elements only come from stars. Two paths lead to dust. Very massive stars die in supernovae that condense elements into tiny solids within cooling ejecta, and lower mass stars swell late in life on the asymptotic giant branch and shed envelopes where grains nucleate. The second path normally takes hundreds of millions of years, a span that seems tight in the earliest times, so the balance tilts towards supernova seeds boosted by rapid grain growth inside dense clouds, where atoms stick to existing particles. The telescope reads this history from shapes. When the continuum between 6 and 12 micrometers slopes upward and then dips near 9.7 micrometers, a shallow trough hints at silicate absorption, the sign of oxygen-rich grains along cool lines of sight. In a few targets, a warmer continuum rises with little structure, the signature of tiny grains heated in fierce radiation. Fields a condition expected when star clusters pack hard light into small volumes. Spatial maps add another layer. In lensed systems, the mid-infrared instrument resolves offsets between the younger star-forming knots and peaks of dust emission, as if winds and radiation have pushed grains outward to the edges of cleared cavities. This geometry mirrors nearby starburst regions, where shells mark the boundary between hot interiors and compressed rims, and it says that feedback began to sculpt into stellar matter early with dust already a participant. By fitting the mid-infrared spectral energy distribution with mixtures of grain types and temperatures, teams infer dust masses that, when translated through gas to dust ratios, point to reservoirs consistent with vigorous star formation. Those amounts imply either efficient dust formation in early supernova remnants or rapid growth by accretion of atoms onto seed grains within dense shielded clouds. The latter path demands high densities and modest temperatures to allow sticking conditions hinted at by bright oxygen lines paired with pockets of cooler gas. Chemistry thus arrives as a choreography between hot young stars and cooler phases that briefly shelter grain growth. Another clue hides in the relative heights of the aromatic bands. In metal poor galaxies nearby, the feature near 3.3 micrometers weakens relative to 7.7 likely, because harsh radiation breaks small molecules. In the earliest galaxies, the pattern sometimes flattens, suggesting a mix where small aromatic molecules survive in denser pockets, or are regenerated quickly in shocks. This hints that the interstellar medium is already patchy with hard light carving openings, while soft shelters persist. Grain sizes matter for more than spectra. Small grains heat and cool gas efficiently by exchanging electrons with photons, altering the temperature balance that sets how clouds collapse. If the first galaxies carry an overabundance of small grains, they may cool differently, steering star formation toward different cluster masses and changing how feedback couples to gas. This in turn can affect how quickly ionizing light escapes into intergalactic space. Dust both blocks and redirects that light. Thin veils absorb energetic photons and re-radiate them in the infrared, while leaving holes through which some ionizing light still flows. Mid-infrared detections therefore speak to the timeline of the end of cosmic fog. Silicate and carbonaceous grains also seed molecules. On their surfaces, atoms meet and combine into hydrogen molecules, water and carbon monoxide, which then join the cooling budget. The telescope observes these consequences indirectly. Where mid-infrared bands rise far infrared to submillimeter lines seen from the ground, such as ionized carbon, often brighten as if grains accelerate the formation of cold dense pockets. Uncertainties remain. Background subtraction in the mid-infrared is delicate, and thermal emission from the telescope must be removed with precision. Template spectra drawn from nearby galaxies may not reflect conditions of the first system, so teams vary. Grain composition sizes and charge states within models, and compare results across independent reductions. The recurring presence of structured bands above the noise and their alignment with expected redshifted positions provide confidence that the signals are real. Even when bands are weak, the warm continuum and the silicate hint favor dust. The broader implication is a recalibration of time. If dust forms swiftly, then light is processed swiftly. The earlier stars do not simply flood space with raw radiation. They rework their neighborhoods into layered media, where grains shape the roots of energy and matter, setting the stage for metal-rich second generations, and for disks where planets will someday appear. The shock is not loud. It is a change in texture. The first pages of galactic history are not smooth and transparent. They are already gritty, already veiled, and glowing, already capable of hiding and revealing at will. The James Webb Space Telescope writes that texture into the record by catching the faint shimmer where molecules flex and grains sigh, and by doing so turns a timeline into a tapestry where chemistry and light intertwine from the start. Temperature, which is only a measure of motion, becomes the quiet key that separates shadow from flame. The telescope uses the mid-infrared instrument to paint the warmth of tiny grains and to hear faint molecular songs, while the longest channels of the near-infrared camera trace young clusters still wrapped in haze. These maps are then set beside ground-based views from the Atacama Large Millimeter Array that tune to long wavelengths where the coldest gas speaks. Across fields crowded with early galaxies, a pattern repeats with patient insistence. Cold veils sprawl as dim blankets, and within them sit compact hearts that shine warmer than their age would suggest. The contrast is not theatrical. It is measured in ratios of filters and in the slopes of continua, but the geometry is striking. A shell that rests at only a few tens of Kelvin surrounds a core whose dust rises to several tens, or even about 100 Kelvin, and the starlight that drives that warmth gathers in knots no more than a few hundred parsecs across. The telescope reads these gradients by comparing brightness in carefully chosen bands. When the flux at a longer mid-infrared wavelength outruns the flux at a shorter one, the color implies cooler dust. When the shorter band pulls ahead, the color tips warm. In maps of lensed galaxies where magnification stretches structure into crescents, the color temperature pivots sharply across small distances. Blue-tinted warmth in the mid-infrared hugs the bright star-forming knots, while redder, cooler colors drape the outskirts in arcs and sheets. The same systems seen by the Atacama Large Millimeter Array, in lines of ionized carbon at 158 micrometers, and in continuums that prefer cold matter, reveal filaments and reservoirs that align with these cool sheets. Warm cores breathe inside a lattice of cold, dense gas. The picture echoes a familiar rhythm from nearby nurseries but plays faster. Young clusters pour out ultraviolet light that charges and shakes the grains, which then radiate in the mid-infrared. Winds and first supernova hollow small cavities. Their edges glow as compressed rims, and farther out the cold survive ready to collapse again. Because these galaxies are tiny and gas-rich, the spacing between warm pockets shrinks, and the temperature contrast grows steep. The telescope also sees places where warmth and cold switch roles. Some galaxies show warm rims around slightly cooler centers, as if star formation ignited in a ring that circles a less active core. Integral field spectroscopy with the near-infrared instrument measures gas motions that swirl around those rings, in ordered patterns hinting that torques and inflow have pushed gas outward into a tight loop where density crossed a threshold and set the ring ablaze. In such cases, the cold lies at the center, awaiting the next inward migration of clumps, while the hot edge races around like a lantern on a wheel. The physics that knits these mosaics is grounded and yet still unfamiliar in pace. Cold gas stays cold because it radiates its energy away efficiently through long wavelength lines, and because dust grains help it trade energy with light. The same grains, when packed near young clusters, heat until they glow. Radiation pressure then adds a soft shove, pushing grains outward and dragging gas with them along low-density paths. Thus, escape routes form where ionizing photons leak into intergalactic space. Those channels can be seen indirectly when the hydrogen line that would normally be trapped by surrounding fog shows a faint red-shifted shoulder. The temperature map and the line profile speak the same language, a porous medium, where hot cores carve vents through cold walls. Magnetic fields and turbulence refine that language. The Atacama Large Millimeter Array detects thread-like shapes that in nearby galaxies trace magnetic scaffolds. While the telescope cannot measure fields directly, the alignment of cold filaments and the regular spacing of warm knots suggest that turbulence decays quickly in the densest layers, allowing gravity to seize control in beads along strands. Each bead becomes a hot core once ignition begins, and each core radiates into the cold until feedback cuts the fuel. The timescales implied by these sizes and luminosities run short no more than a few tens of millions of years for individual bursts, which fits within the tight chronology already pressed by the high redshifts. In a few targets, the mid-infrared spectrum shows a shallow trough near 9.7 micrometers, a hint of silicate absorption, laid over a rising warm continuum. That trough is stronger when the line of sight crosses more dust and is weaker where cavities open. Comparing its depth across a galaxy gives a second view of how cold layers curtain the hot heart. Where the trough deepens, the escape of ionizing light appears weaker in complementary spectra, reinforcing the picture that cold veils modulate the flow of energy outward. The telescope also sees molecular bands that wobble in strength from knot to knot. Where the bands near 6 to 8 micrometers are bright, the cold gas traced by ionized carbon lines is also bright, suggesting that dust surfaces help assemble molecules that then cool the gas further. It is an early feedback loop. Grains seeded by the first explosions become workers that knit more molecules, and those molecules allow the next generation of clouds to condense and feed new stars. The persistence of cold in the presence of fierce radiation raises deeper questions. Why does the cold not vanish wholesale in such small systems? Part of the answer lies in geometry. The hot cores are compact, so their radiation dilutes rapidly with distance. Part lies in replenishment, as inflowing streams deliver fresh, cool gas along filaments that the telescope cannot yet see directly, but that simulations predict. Part lies in shielding by dust that has grown more quickly than assumed. The result is a layered city where cold boulevards bring fuel to bright districts that flare and dim in cycles. The shock is that this city plan appears already drawn within the first few 100 million years. These temperature maps also bear on the growth of central black holes. In a handful of compact galaxies, a point-like nucleus glows very warm in the mid-infrared, and the spectrum carries hard edges that speak of accretion. Around those nuclei, the cold gas seems pinched into spirals or lanes, as if gravity and torque are funneling material inward. If the nucleus feeds while rings of star formation circle outside, then heat from the center can flip temperature gradients and shut off or move star birth. The timing of these flips is a frontier. Longer stares will track whether warm cores fade and cold rims light up again, and whether the nucleus grows while the ring dims. The telescope is methodical. It measures filter ratios with care, cross-checks with spectroscopy, and compares with the Atacama Large Millimeter Array to confirm that cold gas truly sits where the maps imply. The instruments agree often enough to make the thermal contrast a fact rather than an artifact. From this contrast emerges a simple, potent idea. The earliest galaxies are not uniformly hot or uniformly cold. They are patchwork worlds where heat and chill are neighbours, where dark veils cradle bright hearts, and where the route from gas to stars is set by the very grains that both hide and reveal the light. That arrangement, humble in its physical ingredients, rewrites the pace of early growth by making room for efficiency inside shelter. The universe begins not with bare flames, but with hearths that burn within snow. Gravity speaks without light, and the James Webb Space Telescope becomes a microphone pressed to that whisper. In the first deep field, a foreground cluster bends space-time into a slow whirlpool that gathers the glow of more distant galaxies and stretches them into arcs. Those arcs, when measured in detail by the near-infrared camera and traced in repeated filters, do not land exactly where an accounting of stars and hot gas says they should. The positions of multiple images, their separations along the arcs, and the gentle twisting of their internal features conspire to demand additional mass with no starlight. Lens modelers build maps by anchoring each arc to a candidate source, and by adjusting the gravity until the predicted counter-images appear where the telescope actually sees them. The mass that best fits the pattern does not simply follow the visible galaxies in the cluster. It spreads as a smooth backbone, and then lumps into knots that sometimes have no bright counterpart at all. In a few cases, tiny wiggles along an arc, small deflections that change the width or brightness from one knot to the next, insist on substructures with masses far below that of a normal galaxy. Those substructures are like pebbles on a riverbed that do not break the surface, but still ripple the flow. The near-infrared camera, with its ability to resolve the star-forming beads inside background galaxies, amplifies this effect. Because the instrument discerns features inside the lensed images matching those details across multiple images, acts like placing several pushpins into a rubber sheet and asking the model to pass through all of them. The required precision reveals not only the overall pull of the cluster, but also the tug of small dark clumps. When combined with maps of hot gas from X-ray observatories, and with the light of the cluster's own galaxies, the remainder left for the unseen component is unmistakable. The quietly alarming part is how much structure that remainder appears to carry. In cold, dark matter, Theory's invisible particles move slowly and cluster on all scales down to very small masses. In warmer or more collisional versions, small lumps are erased or puffed up. The telescope's reconstructions, grounded by dozens of multiply image sources across a single cluster, lean toward a populous family of small halos. The arcs seem to notice clumps with masses only a tiny fraction of a typical galaxy, and they do so in several independent clusters. Each detection is modest, but together they push the distribution of substructure toward the cold extreme. Beyond the strong lensing regime where arcs curve dramatically, the telescope also detects subtle alignments of galaxy shapes behind less massive lenses, patterns called weak lensing that reveal the average pull of invisible matter in a wider field. Although the telescope's field of view is not enormous, its exquisite shape measurements and its deep detection of faint background sources allow a clean measurement of shear, the tiny stretching that gravity imposes on many lines of sight. The resulting mass maps show filaments that connect clusters to groups, a cosmic web drawn not by light but by geometry. Those filaments often intersect where the clusters sit, and the mass inferred from the lensing outweighs the sum of all visible matter by a large factor. Some clusters are still assembling, and the telescope catches dark bridges, where only a few galaxies travel bridges that nevertheless weigh enough to bend background shapes measurably. In a handful of merging clusters, the telescope's lensing maps and the positions of hot gas diverge in space, with the mass peaks leading or lagging the gas clouds. That separation echoes earlier surprises seen at other wavelengths and is now confirmed at finer scales, strengthening the case that the invisible component passes through collisions with little friction while gas collides and slows. If the unseen mass had strong self-interactions, its peak would also lag, but the lensing says it keeps going. In the cores of clusters, the story becomes even more intimate. The telescope identifies lensed images within only a few kiloparsecs of the central galaxy. To place those images where they are models require a density profile for the invisible mass that may be slightly shallower than the steep curves often assumed, as if heat from infalling galaxies outflows from the central black hole, and dynamical stirring have softened the dark heart. The balance between a sharp cusp and a softer core is delicate, and has implications for the microphysics of the unseen particles. The data do not declare a verdict, but they narrow the range and invite simulations to include the complex push and pull of baryons with greater realism. The telescope also watches galaxy-scale lenses where a single massive galaxy splits a background source into 2 or 4 images. Tiny offsets in the brightness ratios among those images once dust microlensing by stars and intrinsic variability are accounted for point again to dark subhalos that sit inside galactic halos. Because the near-infrared camera resolves the background galaxy into clumps, and because the near-infrared spectrograph can isolate a bright emission line to map one clump at a time, investigators can compare how each clump is lensed and thus triangulate the position and mass of a lurking subhalo. This is a quiet but powerful census that complements the cluster-scale maps and pushes the test of dark matter into the realm of dwarves. Alternatives to an invisible particle, theories that modify gravity at low acceleration, face a harder climb, where complex lens geometries offsets between gas and mass, and the abundance of substructure must all be explained at once. The telescope does not argue. It measures, and the measurements prefer a substance with weight but little light, a substance that clusters into many small knots and that sails through collisions with only gentle self-regard. Yet even within this portrait surprises remain. Some lensed arcs require subhalos seemingly without stars, while nearby galaxies in the same cluster carry more stars than naive models of feedback would allow at similar masses. The scatter is wide. Stochastic processes, early mergers, and varying radiation backgrounds may all sculpt whether a small halo lights up or stays dark. The James Webb Space Telescope, by counting both the lit and the unlit through their gravitational marks, shifts the focus from missing satellites to a measured distribution that includes them whether or not they shine. As the mass maps grow richer, they intersect with the early galaxy story in a loop. If dark matter clumps are abundant, then seeds for early galaxy growth are plentiful, helping to explain the overabundance of bright compact systems at high redshift. If clumps are scarce, that explanation weakens. The current lensing evidence, with its fondness for small structure, threads back to the brightness problem and gives it a scaffold. The shock remains quiet because it arises from fits that place arcs correctly, and from shear fields that match the statistics of thousands of shapes. Gravity's mismatch with light is not a failure. It is the shape of a presence that does not glow. By listening to that presence through the whispered distortions of background galaxies, the telescope offers perhaps the most persuasive glimpse yet of the invisible architecture that underlies the earlier scenes. It is a map that looks like a web woven by a patient hand tugging where no threads can be seen, and it leaves open the nature of the weaver even as it sharpens the weave. Compact hearts in small galaxies glow with a steadiness that belies their age, and within those hearts the signatures of deep gravity begin to surface. The near-infrared camera finds point-like cores whose light profile matches the instrument's sharper shape more closely than any surrounding star-forming knot. The near-infrared spectrograph then ties this morphology to motion-revealing emission lines that are bright and broad. Hydrogen lines shifted into the near-infrared span several thousand kilometers per second, in full width at half maximum a width that exceeds what clustered supernovae normally produce, and that implies gas orbiting near a deep potential. In a few cases, high ionization lines associated with coronal gas emerge above the continuum narrow in some regions and broader in the core, as if a compact engine both lights and stirs its environment. Luminosity and width together feed the simple, virial recipes that convert line kinematics and radiation into mass. The resulting black hole masses land at values that, when compared to the small stellar masses inferred for their hosts, look large by local standards. The ratio between central mass and stellar mass, which in the nearby universe rests near a few thousandths for many systems, appears heightened sometimes by an order of magnitude or more. It is not universal, and uncertainties are real, yet a subset of early galaxies seems to house black holes that are overmassive for the homes that contain them. The mid-infrared instrument adds a layer of heat to this picture. Warm dust in ordinary star-forming regions emits with a smooth rise that grows toward longer wavelengths, but in several nuclei, a separate hotter component peeks through in the near to mid-infrared range as if grains sit close to the sublimation edge and re-radiate the energy of accretion. Where that continuum is strong, the spectral slope in the longest near-infrared filters flattens, and aromatic molecular bands weaken near the center as if harsh radiation suppresses the complex hydrocarbons that otherwise survive in sheltered pockets. The spatial pattern of this suppression deepest in the core and easing outward maps an energy source more concentrated than even tight clusters of young stars. Obscuration complicates the view and enriches it at once. Some nuclei show weak or undetected soft X-rays in supporting observations, while still radiating strongly in the mid-infrared, a combination that suggests column densities high enough to hide the hardest light. The near-infrared spectrograph answers by finding high ionization lines that penetrate dust more effectively, and by measuring line ratios that fall in regions usually associated with active galactic nuclei, rather than with ordinary H2 regions. In a few cases, the hydrogen line appears in both a narrow component tracing star-forming gas and a very broad base tracing gas close to the central object, a two-layered signature that separates engine from host. Where a foreground cluster provides magnification, the telescope leverages that gift-to-pass structure that would otherwise blur. The near-infrared camera isolates a nuclear spike and reveals faint starlight around it. The spectrograph places its slit or its integral field on each part and separates the blended spectrum into a narrow metal-enriched host component and a hard, sometimes feature-poor nuclear continuum. Correcting for magnification and for slit losses yields luminosities that, when translated through the Eddington limit, imply either high accretion rates onto modestly large black holes or moderate accretion rates onto surprisingly large seeds. Either option compresses time. If the seeds came from the collapse of very massive metal-free stars, they would begin small and require persistent near-limiting inflow to reach the inferred masses within a few 100 million years. If the seeds formed by direct collapse of dense, pristine gas clouds that fragmented only weakly, they could start large and need fewer growth cycles, but they would demand special conditions where cooling and angular momentum loss occur without birthing ordinary stars first. The telescope cannot yet settle the origin, but it draws boundary lines that each theory must cross. Outflows carry the same argument into motion. In several compact systems, the near-infrared spectrograph maps the profile of doubly ionized oxygen across the face of the galaxy, and finds blue wings and red wings that betray gas pushing outward at several hundred to a few thousand kilometers per second. The mid-infrared instrument shows a brighter warm continuum on the side where the blue wing dominates as if dust in the near-side wind is heated on its inner face. These flows can lift gas from the shallow potential wells of small hosts and may help regulate both star formation and further feeding of the nucleus. They leave cavities and cones that line up with faint deficits in aromatic bands, drawing a geometry of feedback that is already familiar in the local universe, but now appears miniaturized and accelerated near cosmic dawn. Variability offers a quieter test. Repeated imaging over months to years in the observer frame reveals gentle flickers in the compact cores, while the surrounding starlight remains steady within errors. Such twitches are consistent with stochastic accretion, as clumps of gas cross the last stable paths and fall inward. The amplitude is small, masked by distance and by dilution, yet it supports the idea that an engine, not only a starburst, drives the nucleus. Host galaxies tell a complementary story through their modest sizes and by kinematics that sometimes already show ordered rotation. The mismatch between black hole mass and stellar mass could ease as bursts build the host, but the snapshot the telescope provides still demands early efficient seeding. Even more, the presence of an active nucleus inside a tiny rotating system suggests that early disks can already supply angular momentum transport and funnel gas inward through clump migration weak bars or torques from minor companions. This synergy between rapid disk assembly and rapid black hole growth narrows the acceptable histories to those that allow both to proceed in parallel. Alternatives receive careful attention. Extremely dense young star clusters can harden spectra and broaden lines, but they struggle to produce the hot dust signatures and high ionization features concentrated so tightly in the core. Shocks from stellar winds can mimic some coronal lines, yet their spatial pattern typically follows star-forming knots rather than a single spike. Teams therefore use integral field spectroscopy to map line diagnostics across each galaxy, looking for cones and ionization gradients that often betray an active galactic nucleus. Light profiles are decomposed into a point source and an extended component, and the residual host brightness is checked against expectations from star formation indicators such as nebular lines and aromatic bands. Across this suite of tests, a consistent subset of early galaxies remains compact, bright, warm-cored, kinematically hot at the center, and overmassive in their central engines relative to their fragile homes. The shock remains quiet because it is a matter of proportion. Engines appear before the chassis is complete. Beacons light while the towns that will one day obey them are still scaffolds of gas and young stars. The James Webb Space Telescope registers those beacons by the width of lines, by the warmth of closest dust, by the subtle dimming of molecules that cannot survive in the glare, and by the way gravity makes a point of light outshine a city. From these measurements rise the questions that point inward. How large were the first seeds? How smooth or clumpy was their food? And how often did early disks trade their spin for the growth of a dark central heart? Close to home, the scaffolding of starbirth stands in clear air, and the James Webb Space Telescope uses nearby clouds as laboratories to test the rules it inferred from distant youth. The near-infrared camera frames towers and curtains of gas in the Eagle Nebula, and along the edge of the Carina Nebula, where ionizing light from massive stars gnaws at cold walls and leaves pillars with sculpted faces. Along those faces, bright knots stud the rims like beads pressed into clay, and from many of those knots, hairline jets lance outward in opposite directions, narrow and straight, ending in faint shocks where the flow meets denser clumps. The mid-infrared instrument layers warmth and chemistry onto these shapes. Aromatic molecular bands climb along the sunlit sides of the cliffs, tracing carbon-rich compounds that light up where radiation grazes dense surfaces, while deeper inside the continuum warms gently, where tiny grains soak up scattered photons. The telescope sees protoplanetary disks cradled in the shadows, their lines of dust stretched into tails that stream away from the brightest stars, a signature of evaporation by hard light that steals the outer layers while inner regions persist. In the Orion bar, a nearby front where hot ionized gas presses against a molecular cloud, the integral field unit maps a crisp sequence from ionized hydrogen to warm atomic layers to molecular hydrogen, and onward to deeper, cooler carbon monoxide and water ice. The gradients unfold across distances that a spacecraft can measure in light weeks, and the relative brightness of lines and bands matches a narrative in which radiation does not simply erase clouds, but sculpts them into layered shells that foster and then erode star formation. In the darkest crevices of the Chamaeleon region, the mid-infrared instrument reads the deepest absorption bands of carbon dioxide, ice water, ice, and complex organics along lines of sight toward faint stars, revealing that dust grains carry mantles dense with frozen chemistry even before large stars arrive. These mantles provide surfaces on which molecules assemble, so that when a young object lights its envelope, already contains a library of compounds that seed further reactions. The near-infrared camera catches dozens of infant stars in these same fields, each wrapped in a disk whose inner edge glows, where starlight heats the rim. In a few shadows cast by warped inner disks sweep across the outer parts, like the hands of a clock, as the system rotates, proof that geometry inside these small worlds changes on human timescales, and that small torques can redirect inflow. In one corner of a nearby cloud, the telescope resolves a spiderweb of narrow filaments that converge toward a hub where several bright sources cluster. The thickness of the filaments is nearly uniform, and their spacing relative to the sizes of the new stars resembles a pattern familiar from gravitational instability in sheets now made visible by the interplay of emissions from molecular hydrogen, warm dust, and faint atomic lines. Gas creeps along the filaments into the hub at speeds of only a few kilometers per second, yet the steady feed builds a central mass that then launches jets and outflows which blow cavities back into the web. The cavities outlined by aromatic bands and warmed by dust on their inner walls intersect and form rings where multiple flows push together, and those rings in turn host new knots that begin to collapse. Feedback and formation run side by side, not in separate chapters. Local clarity unsettles distant assumptions because it shows just how many channels can couple to make or unmake a star. Shocks at the heads of jets compress gas and trigger more collapse, but they also heat and ionize, making halos where molecules cannot survive until cooling rebuilds them on dust surfaces. Radiation eats at edges, but it also draws sharp density peaks, where a compressed front folds into a ridge, and in those ridges gravitational instability returns. Magnetic fields thread the filaments, organizing the flow into lanes that resist bending, and that guide jets along preferred directions. The Atacama Large Millimeter Array complements these views with cold gas maps that show the same filaments in emission from ionized carbon and carbon monoxide, while the telescope's mid-infrared bands reveal where dust changes charge and size across each front. Together they show that the interstellar medium is not a single fluid, but a set of interleaved phases that exchange energy and matter quickly. When the telescope carries these insights back to the high redshift puzzles, several habits of thought begin to shift. Bursty star formation in compact galaxies no longer needs to rely solely on sudden floods of gas. It can arise naturally from the way filaments feed hubs, and from the way outflows carve cavities that later gather their own rims of collapse. The early presence of dust gains a mechanism in the rapid growth of mantles inside shielded pockets, which the telescope sees directly in ice absorptions toward nearby background stars. The quiet order found in youthful disks far away gains an analogue in the surprisingly sharp kinematic layers of the Orion bar, where rotation and pressure carve lanes only a few light-years long, that nevertheless channel gas with discipline. Even the missing spectral lines at great distance find echoes in local patchiness. Along some sightlines in nearby pillars, ionizing photons leak through gaps and leave nebula lines weak relative to continuum, while a few arc-seconds away a denser knot glows with the missing lines in full. The telescope's integral field maps, when smoothed and scaled to the coarse resolution that distant galaxies impose, look like the mixed spectra that puzzled teams at redshift 10 and beyond. Perhaps the local scenes suggest the early universe hid similar patchwork inside each tiny galaxy, with some clumps porous, and others cloaked, some lines muffled, and others bright, a mosaic, that averages into the odd ratios now measured across cosmic time. Protoplanetary disks bring the story down to smaller scales that still carry lessons outward. In the Carina field, disks near massive stars illustrate how a harsh radiation bath strips mass, quickly potentially altering the eventual architecture of planets, while disks deeper in shadow show richer aromatic bands and thicker ice signatures, as if their chemistry has more time to build complexity. If such environmental dependence holds in the first galaxies, then the earliest planetary systems may have been shaped by the same proximity to intense clusters that now sculpt disks nearby, biasing where thick atmospheres or water-rich worlds could form. The telescope does not force the analogy. It lets the eye travel from a jet that drills a thin channel, through a cloud to a ring where two cavities meet, to a hub where filaments converge, and asks what happens if these motifs are scaled down in time and up in density in a young compact galaxy. The answer is a framework that tolerates speed. Cold gas can organize quickly into lanes. Dust can assemble mantles that speed cooling. Jets can puncture escape routes for ionizing light. And radiation can both suppress and ignite depending on how it strikes a surface. The calm shock in these scenes is not that nature invents new physics at high redshift, but that familiar physics operates efficiently when fuel is abundant and distances are short. By rethinking stellar nurseries in the nearby sky, with resolution that makes their architecture undeniable, the James Webb Space Telescope equips the study of early galaxies with a set of tested blueprints. It becomes easier to believe that tiny systems could look orderly, while still being driven by bursts that spectra could lack lines without trickery, and that chemistry could mature early on the backs of grains. The open question is how these nested processes scale with gravity and time as the universe steps from the neighborhood to the edge of the observable past. Starlight slides through alien air, and the telescope turns those faint losses into a ledger of molecules. During a transit, when a planet passes in front of its star, a thin ring of atmosphere imprints extra dimming at wavelengths where gases absorb. The near-infrared imager and slitless spectrograph in its single-object mode holds the star steady and spreads its light into a rainbow, while the near-infrared spectrograph takes over for finer features, and the mid-infrared instrument adds longer tones where heavier molecules sing. A hot Saturn mass world catalogued as WASP 39b becomes the proof of principle, and then the first surprise. The transmission spectrum shows deep water bands, and more strikingly, a strong feature at about 4.3 micrometers that aligns with carbon dioxide. The shape and depth of that band require a high abundance and retrievals that fit the spectrum point to an atmosphere enriched in heavy elements compared to its star. The same planet delivers a subtler ridge near about 4.05 micrometers that fits sulfur dioxide, a molecule not expected in equilibrium at the measured temperatures. Its presence implies active photochemistry, where hard starlight breaks apart hydrogen, sulfide, and other carriers and drives chains of reactions that stitch sulfur and oxygen into new partners. The signal arrives not as drama, but as a clean valley and a clean peak repeated across multiple visits, and it marks the first clear detection of a photochemical product in an exoplanet atmosphere. Other giants extend the catalogue of patterns. A very hot Jupiter named WASP 18b reveals powerful carbon monoxide and a muted or absent methane signature, a combination that shouts disequilibrium because high temperatures and vertical mixing keep methane from taking its expected share of carbon. Water appears again, but not always with the same strength as hazes and clouds lift and flatten the spectrum at some wavelengths. Those clouds are not made of water droplets in these hot skies. Instead, they form from silicates, metal oxides, or more exotic condensates that nucleate on seed particles and spread into global mists. The telescope senses their hand in a raised floor of opacity that reduces the contrast of molecular lines and in color-dependent slopes that rise towards shorter near-infrared wavelengths. The mid-infrared instrument then picks up where haze is thin, revealing carbon dioxide, and sometimes hints of carbon monoxide deeper in. With each world, the balance between molecules shifts, and with it the implied deep chemistry and the way the air moves. The transmission method favors puffy atmospheres, so the telescope also turns to smaller planets, where the signal is meager but the stakes are high, around the cool star named TRAPPIST. Once several Earth-sized worlds march in tight orbits, and their transits give the telescope a chance to test whether thick hydrogen-rich envelopes survive under such light. For TRAPPIST-1b and TRAPPIST-1c, the near-infrared spectra emerge almost flat after careful removal of star spots and flare noise. A flat spectrum means that if an atmosphere exists, it is either very thin or made of heavy molecules with small-scale heights, or it is masked by clouds so high and opaque that all wavelengths dim the same. The absence of sweeping hydrogen features suggest that the earliest expectations of large, low-density envelopes for these rocky worlds are unlikely. That non-detection is not a defeat but a boundary one that guides models of atmospheric escape and volatile delivery. On a temperate sub-Neptune called K218b, the telescope measures a set of bands that include water and a tentative feature near 3.2 micrometers that some fits assign to hydrogen cyanide, a tracer of carbon-rich chemistry under disequilibrium. The possibility remains debated because clouds and hazes can mimic subtle arcs, but the data allow a family of solutions where the atmosphere carries more carbon relative to oxygen than the star does. If such ratios hold in other sub-Neptunes, they may point to formation zones beyond the water ice line followed by inward migration, or to strong loss of oxygen, bearing species during long epochs of irradiation. The telescope adds another angle by watching secondary eclipses when the planet slips behind the star and its emitted and reflected light vanish for a moment. The depth of that step across wavelength builds an emission spectrum that constrains temperature profiles, and when these are combined with transmission spectra, a more complete picture emerges. On WASP-39b, the emission data suggest a thermal structure with an inversion in some layers consistent with absorbers like sulfur dioxide and carbon dioxide, capturing starlight high and re-radiating it. On WASP-18b, the dayside glows so hot that molecules struggle to survive near the substellar point, and emission features shift into absorption or disappear, reinforcing the story that chemistry is not at rest. Phase curves where the telescope follows a planet through many orbital phases add winds to chemistry by revealing how heat shifts from the day side to the night side. Some worlds move energy efficiently, blunting the day-night contrast, while others clamp heat near the star-facing hemisphere. The way water band depths change with phase shows where clouds form and where they evaporate, often piling up at the western limb as winds blow hot gas into cooler dusk. Through all of this, the telescope must undo the temper of the host stars. Cool dwarfs carry spots and faculae that alter the stellar spectrum and can imprint false features if uncorrected. Teams observe out of transit baselines, monitor variability, and fit joint models of stellar surfaces and planetary atmospheres. Residuals shrink and confidence grows in the main signatures. The oddities remain even after caution. Sulfur dioxide at high altitude on WASP. 39b requires photons with energy to drive sulfur pathways and a circulation that lofts products faster than they can be destroyed. Carbon dioxide levels imply metal enrichment that echoes the heavy element richness found in the cores of solar system giants, but perhaps pushed higher. Methane scarcity on several hot Jupiters and sub-Saturns speaks of intense mixing or dayside temperatures that cross chemical boundaries. Hydrogen cyanide candidates on a sub-Neptune beckon with the prospect of carbon-rich regimes that alter cloud composition and radiative balance. Flat spectra on rocky worlds around a cool star carry the quiet shock that a simple hydrogen blanket is gone, leaving either naked rock or heavy air. The implications spill forward to habitability frameworks. Photochemistry that produces sulfur dioxide in one regime could produce different oxidants in cooler regimes, changing how biosignatures are framed. High metal enrichment and altered carbon to oxygen ratios steer, which condensates form and where clouds sit, reshaping climate. Clouds that mute transmission can still sculpt surface conditions by reflecting starlight or trapping infrared radiation. The James Webb Space Telescope does not find life. It builds the physical stage on which that question will be posed. By stacking thousands of photons into bands that tie directly to molecular bends and stretches, it shows that alien skies at once follow rules and refuse simplicity. The quietly shocking part is not that molecules are present, but that they arrange themselves into climates already distinct from expectations built on equilibrium tables. Air is not a passive filter. It is a living chemistry set lit by a star, and the telescope has begun to read its labels. Weather that should not exist rises from the data as light curves turn into moving maps. The telescope watches a planet complete an orbit and records the star plus planet brightness. As a function of phase, then subtracts the star during secondary eclipse, when the planet slips behind, and adds the planet back as it reappears. The curve becomes a thermometer laid along longitude. On several hot giants, the peak of thermal emission does not sit at the substellar point, where noon is eternal but slides eastward by tens of degrees, a sign that fast winds carry heat before it can re-radiate. General circulation models had predicted a broad eastward equatorial jet on tidally locked worlds, yet the measurements sharpen the picture. The jet is narrow, the hotspot shift varies with wavelength, and the night side is darker than many expectations allowed. On a well-studied hot Jupiter, the mid-infrared instrument phase curve shows a day that blazes and a night that cools so sharply that water molecules likely break apart on the day side only to reform on the night side, where temperatures drop a chemical shuttle that itself transports energy. The near-infrared spectrograph adds a complementary phase curve in water and carbon-bearing bands, and the depth of those bands changes with longitude, in a way that argues for high-altitude clouds on the night side and for cloud holes on the dawn limb where clear windows let deeper, hotter layers radiate. The winds that move this heat are not gentle breezes. By matching the longitudinal shift of the thermal peak with radiative timescales set by pressure and composition, the inferred speeds climb to a few kilometers per second near the photosphere, a super-rotation that circles a world in less than a day. Yet the story refuses uniformity. On a particularly hot giant with stronger radiation, the hotspot lies closer to the substellar meridian at short wavelengths, while it still drifts east at longer wavelengths, as if magnetic drag or short radiative timescales pin the uppermost layers while deeper levels keep flowing. In another case, the peak leans slightly westward, a rare reversal that models can produce only when clouds load the morning limb with reflectivity, or when night-side condensation and day-side ionization reshape the balance of momentum and drag. The telescope turns phase curves into weather, not only through brightness changes, but also through spectral changes. As a planet rotates the transmission spectrum during ingress samples the evening terminator and during egress samples the morning terminator, differences between the two reveal how clouds and chemistry vary with longitude. In several systems, the morning limb carries stronger signatures of metal oxides and silicate condensates consistent with night-side cooling that grows mineral clouds which then sweep into dawn. The evening limb often looks clearer as grains that condensed overnight evaporate into invisible gases before crossing the substellar line. The mid-infrared instrument sees silicate features shift in subtle ways with phase, while the near-infrared imager and slitless spectrograph watches the slope of the continuum rise at the limb where small particles scatter more efficiently. Even the color of the thermal emission speaks. At wavelengths tied to carbon dioxide, the dayside glows deeper than the nightside, but the ratio between dayside and nightside brightness shrinks compared to wavelengths tied to water, because carbon dioxide sits higher in the atmosphere where winds move heat more quickly. This layering turns the phase curve into a vertical probe. Short wavelengths tied to deeper, hotter layers show larger day-night contrast, while longer wavelengths, or strong molecular bands tied to higher, cooler layers, show smaller contrast and larger hotspot shifts. The telescope also measures eclipse ingress and egress with such precision that brightness maps emerge across the dayside. For one giant world, the map reveals a dayside cold spot at high latitude that simple models had not predicted, perhaps a vortex where waves pile up and lift air, allowing cloud tops to cool and brighten the contrast with the surrounding desert of heat. In another, a bright ring separates a very hot inner region from a cooler outer hemisphere, a structure reminiscent of a thermal inversion capped by a blanket of high-altitude absorbers that trap starlight and re-radiate it from a layer disjoint from the deeper heat engine. Nightside spectra demand clouds. Many hot giants show nightside emission that is both faint and blue in the mid-infrared, as if small grains scatter and hide the warm layers, while the water and carbon monoxide features flatten. Condensation chemistry provides candidate silicate clouds, aluminum oxide clouds, titanium oxide clouds at the coldest parts, all carried by winds into belts and patches. Where the phase curve is multi-wavelength, models retrieve cloud particle sizes that differ between morning and evening, with smaller grains at dawn that raise the short wavelength opacity, and larger grains at dusk where coalescence and partial evaporation reshape the size distribution. Mineral rain becomes a literal phrase as droplets or grains form on the night side and then evaporate as they cross the unending noon, closing a cycle of rock in the sky. Magnetic fields deepen the intrigue. At the highest dayside temperatures, alkali metals ionize and free electrons couple the flow to magnetic tension. The resulting drag shortens wind paths and can move the hotspot back toward the substellar point at the top of the atmosphere, while leaving deeper layers freer to race east. The telescope's layer-dependent hotspot shifts fit this mixed regime better than a single wind field ever did. In cooler sub-Neptunes, the weather writes a different grammar. Phase curves show muted day-night contrasts, but strong limb-to-limb changes in spectral features suggesting patchy high clouds that persist even under moderate irradiation. In one case, a feature near 3.2 micrometers grows on the night side relative to the day side in line with hydrogen cyanide that forms in cooler, more carbon-rich layers and is destroyed or diluted on the hot face. Even rocky worlds whisper weather in the negative. Flat transmission spectra around compact cool stars argue that any residual atmospheres must be thin or heavy, and if heavy they likely circulate sluggishly under high molecular weight, building sharp day-night boundaries where heat piles up without spreading. The telescope cannot yet see thermal phase curves for those tiniest targets, but the absence of hydrogen-rich signatures already narrows their climates. Every curve tests the models, general circulation codes that include radiative transfer chemistry that moves with the wind cloud, microphysics that condenses, grows and evaporates, and magnetic drag that rises with temperature now stand against data that slice the atmosphere by wavelength, longitude and sometimes latitude. The result is that some ingredients must be promoted from optional to essential. Cloud formation and destruction cannot be a static deck. It must be a living field that answers to temperature swings of hundreds of Kelvin across a single planet. Chemistry cannot be locked to local equilibrium. Transport and photolysis must run in step with advection. Magnetic effects cannot be hidden in a simple drag term. They must reflect height and composition. The shock is quiet because it rides inside smooth curves. A few parts in 10,000 of starlight modulated over hours reveal winds the speed of sound multiplied several times, clouds made of rock, and nights that glitter with molecules that should not survive the day. The James Webb Space Telescope, by holding a planet in its gaze from dusk through noon to dawn and beyond, makes weather a measurable property of worlds that until now were only points. It shows that the sky is a machine with many gears, and that on other worlds those gears mesh in arrangements that surprise because they work so well. Elements become a clock, and the telescope learns to tell time by their ratios. The near-infrared spectrograph opens the rest frame optical windows of very young galaxies and turns blended glow into specific lines where hydrogen recombination sets a baseline and where oxygen, neon, nitrogen and sulfur trace how stars have already cooked their surroundings. Doubly ionized oxygen compared against singly ionized oxygen and against hydrogen beta and hydrogen alpha fixes the temperature of the gas and its richness in heavy elements, while weaker auroral features adjust that temperature upward or downward until the puzzle pieces lock. In the best spectra, a green oxygen line that would live at about 501 nanometers in the laboratory arrives, shifted into the near-infrared, and its height together with its paired lines places the metallicity at fractions of the solar value that nevertheless are not negligible. The mid-infrared instrument adds further anchors with fine structure lines from doubly ionized neon near 15.5 micrometers, and from doubly ionized sulfur near 18.75 micrometers, transitions that care less about dust, and that sharpen abundance estimates when optical depth and geometry complicate the view. From these layered measures a narrative of time emerges. Alpha elements such as oxygen, neon magnesium and silicon are forged in short-lived giants that explode quickly, while much of the iron peak arrives in white dwarf detonations that wait sometimes for hundreds of millions of years before lighting. If the ratio of alpha elements to iron stands high, the clock points toward youth in chemical terms, even if the galaxy is already busy and bright. Early James Webb surveys find exactly that. In many compact systems at very high redshift alpha elements flourish, while clear iron traces remain modest, as if core collapse supernovae have written the first chapters with a fast hand, and the delayed type of explosions has not yet had time to add its iron. The metallicity itself, even when only a few tenths of the solar value, is quietly startling at such early times, because it requires at least one generation of stars to have lived and died, and to have mixed their products into gas that is now forming the next round. Yet the ratios add nuance beyond a single headline. Nitrogen speaks with two voices, one tied to massive stars that make primary nitrogen even when metals are scarce, and another tied to intermediate mass, stars that build secondary nitrogen in shells that are expelled later. Where the ratio of nitrogen to oxygen rises above the simplest expectations for a pristine burst, the telescope hears an echo of prior cycles or prolonged growth. A number of early galaxies show exactly that behavior nitrogen to oxygen ratios that are not low paired with strong oxygen lines that mark hard radiation fields. The combination implies at least a step and a half of history inside a few 100 million years. Carbon to oxygen ratios add another hand to the dial. The mid-infrared instrument senses the strength of aromatic bands that ride on carbon-rich species, and when those bands appear alongside robust oxygen lines and weak ion proxies, the pattern points to dust growth and to complex chemistry that follow quickly after the first core collapse explosions. Dust itself is a record keeper. Silicate absorption near about 9 7/10 micrometers deepens along some lines of sight, declaring that oxygen has already been locked into grains, while carbon-rich aromatics outline where the radiation field grazes dense interfaces. Because grains grow on metal, their presence tightens the chronology further, saying that the earliest enrichment was not only swift, but also efficient at seeding surfaces where molecules form and cooling accelerates. Spatial structure writes marginal notes onto the same page. In a few lensed galaxies, the magnification separates individual star-forming clumps, and the spectrograph measures that central knots are slightly richer than their outskirts, a gradient that would arise if cold low metallicity filaments feed the edges, while repeated bursts in the core build heavy elements, and then share some of them outward through winds. Other systems show flat or even inverted gradients, a sign that outflows and mergers have stirred metal-rich gas over small scales, erasing the expected pattern. Kinematics join chemistry to decide what escapes. Oxygen lines often broaden and lean to shorter wavelengths, where winds are strong, while nitrogen features remain narrower, suggesting that the hottest, freshest metal load rides outward in fast shells, while older layers linger. In the shallow gravitational wells of tiny hosts, such winds can carry away a significant fraction of metals, delaying the rise of iron that would otherwise follow when delayed explosions arrive. The clock, therefore, has gears that slip because the same burst that makes alpha elements can throw them into space, lowering enrichment locally even while raising it globally. The telescope must guard against false timepieces. Electron temperatures inferred from faint auroral lines need high signal-to-noise. When those lines fall below detection, calibrations drawn from nearby galaxies can bias metallicities high or low. Teams therefore insist on multiple indicators in the same objects near infrared oxygen lines, mid-infrared neon and sulfur. The slope of the continuum across the Balmer break, and when possible, faint iron lines in the rest optical that creep into the longest near-infrared wavelengths for the most ancient targets. The different answers are reconciled with models that account for geometry, for clumpy escape of ionizing light, and for dust that can muffle some transitions while leaving others intact. When the pieces agree, they underline a shared conclusion. Many galaxies within the first few 100 million years carry alpha element to iron ratios that signal rapid recent making, nitrogen to oxygen ratios that hint at layered histories rather than single flashes, and dust signatures that say chemistry and cooling have already matured enough to build grains and mantles. In a few cases, the continuum carries a Balmer break strong enough to suggest an older population beneath a new burst, pushing the onset of star formation very near to the beginning and compressing the allowed timeline for the first enrichment even further. The shock is not painted in bold colours. It is written in consistent ratios that all lean towards speed. Time as told by elements seems to have run fast in those early halls, with generations stacked more tightly than many models had assumed. That tempo does not overturn the broad story of structure rising from small to large. It refines the pace and adds the knowledge that chemistry can keep up with gravity when fuel is plentiful and distances are short. The James Webb Space Telescope reads this clock by counting the bright lines and the quiet dips, by mapping gradients across magnified arcs, and by letting dust whisper where metals have gone. It finds a universe that does not wait for comfort before forging its inventory, and it leaves open how that urgency will echo in the later making of planets, and of the atmospheres that someday may hold a different kind of story. Repetition becomes the sternest teacher, and the James Webb Space Telescope submits its strongest claims to cycles of scrutiny, where instruments trade roles, angles pivot, and time itself is used as a calibrator. Deep fields are retaken at alternate roll angles so that diffraction spikes rotate while the sky stays still, and sources that once hugged the spokes of the point spread function, keep their shapes after rotation, softening the suspicion that glitter became galaxies. Dithers march the scene across detectors to average intrapixel quirks and to break the memory of bad columns. Stacks assembled with stricter or looser masks alter noise at the edges, but do not erase the compact smudges that anchor the earliest counts. Independent teams rebuild flat fields from on-sky data, extend dark current baselines, and tame the slow wander of 1/f noise with filters that respect real structure. Statistics shift in the small digits, yet faint arcs and tiny knots persist where they first appeared. The near-infrared spectrograph replays key targets with alternate gratings, with narrower or wider slits, and in integral field mode so that a line first seen along a single slice is caught again as a map. Wavelengths nudge with updated calibrations, but hydrogen and oxygen arrive where distance requires and early redshifts remain early. The mid-infrared instrument repeats slitless spectra with reversed nods and fresh background fields to subtract the soft glow of interplanetary dust. Aromatic bands and silicate troughs weaken slightly under stricter skies and strengthen slightly under laxer ones, but their pattern of positions and ratios does not go away. Pointing jitter is measured from bright stars and injected into end-to-end simulators. The simulated blur alone fails to conjure the chain of overbright sources unless those sources already live in the input sky. Ghost grating scatter and internal reflections are hunted by sliding stars across the field and by comparing positive and negative orders. A few artifacts earn removal along certain angles, yet the principal anomalies survive the purge. A year passes. The observatory breathes with seasons calibrations sharpen, and repeated fields are compared to their younger twins. Photometry drifts by small amounts, but the bright tail of the early galaxy luminosity function refuses to fold back to comfort. Parallel programs with the Hubble Space Telescope pace the same clusters in bluer bands to expose cool stars that could masquerade as distant sparks. Some imposters are unmasked and subtracted, the remainder are galaxies, and their near-infrared colours still point beyond redshift 10. Ground-based arrays weigh in. The Atacama Large Millimeter Array traces ionized carbon in a subset of the brightest systems, and finds cold gas where the near-infrared light says it should be. Adaptive optics on large mirrors split starlight and line light into separate needles of focus. Coordinates match lines are real, and the mass required by lens models stays high. Phase by phase, objects that should have withered under scrutiny survive, and yet something else remains that resists comfortable fitting residual patterns that repeat across instruments and teams. The brightness distribution still leans toward an overabundance of compact luminous systems within the first few 100 million years. Spectra still carry missing or muted lines in places where templates drawn from later epochs would expect a fuller chorus. A minority of tiny hosts still cradle nuclei that look overmassive when widths and warmth are turned into central masses even after the most conservative assumptions. Thermal mosaics still show cold veils wrapped around hot cores at scales that echo local nurseries but run on compressed times. Phase curves of hot giants still reveal winds that outrun sound, and clouds that cycle rock across a day. The telescope refuses to be the cause of these patterns. It behaves as an honest witness whose quirks can be modelled and whose errors can be bounded, and when those bounds tighten, the cosmos retains the same story. Forward modelling flips the logic fake skies are hurled through the full pipeline with cautious growth tracks with lens populations that suppress small structure, with star formation histories that avoid bursts. The recovered catalogues from such skies do not resemble the real ones, no matter how selection effects are tuned. They lack the tail of very bright, very small systems. They fill in spectral lines that in reality appear suppressed. They underproduce warm nuclei and overproduce smooth cores. Only when the input population is allowed to be clumpier, burstier, and more strongly lensed by abundant small halos do the mocks approach the data, and even then the match is incomplete. Stacking adds another verdict. When images are aligned on the faintest candidates and averaged, a low surface brightness envelope appears at levels consistent with tiny disks rather than with point-like artifacts, and the radial profile changes with wavelength as expected for a mix of young stars and dust. When spectra of the most extreme objects are stacked in the frame of oxygen peaks, the missing hydrogen line remains weak, as if the average path out of a galaxy and through surrounding fog still blocks its escape. Even the background between sources, the soft glow that carpets deep fields, offers a small but steady hint. Its fluctuations carry a spatial correlation that aligns better with many faint compact emitters than with a smooth, slowly rising population. Cosmic variance is tested by moving to new parts of sky far from the first. Numbers wobble within errors as they must, but trend lines hardly bend. A skeptic might still ask whether a subtle systematic weights, unrecognized perhaps a minute crosstalk in detectors, or a quiet nonlinearity at the faint end. Yet the same skeptic must then explain why such a flaw would grow in spectra. Taken with a different instrument in maps made at longer wavelengths and in lens reconstructions that know nothing of detectors, the persistence of the anomalies becomes its own measurement. It sets a floor on how much theory must move. The early universe seems able to assemble bright compact galaxies faster than expected, to sculpt ordered motion sooner, to grow warm dust and complex molecules rapidly, and to light central engines that outpace their homes. The shock is not a headline, it is a residue that remains after every subtraction. The James Webb Space Telescope, by surviving its own cross-examination, hardens that quiet shock and points the way forward. Keep measuring, keep repeating, and let what refuses to vanish. Write the next set of questions. The map ahead draws itself from what refuses to fit, and the James Webb Space Telescope traces routes that other instruments and future campaigns can walk. If bright compact galaxies gather too soon, then deeper, wider near-infrared imaging must measure the faint end with equal care, because the shape of the luminosity function will decide whether bursts merely lift a few systems or whether the entire population rose on a stronger tide. Mosaic fields that step beyond rich lenses into blank sky will test whether magnified lines of sight biased the first counts, while targeted lens programs that exploit clusters with many multiply image sources will refine the census of small halos that nip arcs into ripples. Integral field spectroscopy will push from isolated slits to full velocity maps, so that rotation curves and turbulent line widths can separate ordered disks from violent mergers and reveal whether early thinness is a stable state or a passing frame. Where hydrogen lines are weak or missing, the spectrograph will lean on oxygen, nitrogen, neon, and sulfur to triangulate metallicity and ionization, and multi-epoch programs will search for the reappearance of hydrogen emission along sight lines where local winds or patchy cosmic fog briefly open channels. Mid-infrared observations will return to the same galaxies across seasons to see whether aromatic bands and silicate signatures brighten or fade as bursts light and cool, because a living dust budget would reveal how grains grow break and seed molecules under truly young conditions. The Atacama Large Millimeter Array will pair with the telescope to weigh cold gas and to track ionized carbon across filaments that feed the tiny disks, while future arrays at longer wavelengths promise to draw the earliest riverbeds of inflow directly. If overmassive nuclei nest inside fragile hosts, then time and resolution become the deciding tools. Repeated spectra will search for gentle changes in line widths and continuum slopes that betray flicker near the central engine, while even finer lensing magnification will resolve the edges of cones where outflows carve holes in dust and hurl metals outward. The balance between feeding and feedback belongs not to a single mechanism, but to a conversation between clumps, bars, rings, and gravity itself, and that conversation will be recorded by velocity fields that measure small non-circular motions, and by mid-infrared color maps that sketch the warmth of dust along lanes that lead inward. If early dust and molecules arrive before comfort, then the chemistry of that speed will be checked by catching the same galaxies in absorption against background sources, and by using the longest near-infrared channels to reach faint ice bands at high redshift. In nearby clouds, continued mapping of ice toward deeply embedded stars will refine how quickly mantles thicken and which radicals accumulate. Then those rules will be carried back to arc-lensed knots, where similar processes must run in compressed time. If gravity's web is as pebbled as the arcs insist, then cluster catalogues with hundreds of multiply image systems will push substructure statistics down toward masses where particle models diverge. Weak lensing over broader fields with the telescope's sharp shape measurements will chart filaments that feed forming clusters, and comparison with hot gas maps will test how invisible matter glides while baryons collide. Where cores in clusters look slightly softened, joint fits that include central black hole feedback and the stirring of infalling galaxies will decide whether heat or microphysics flattens the profile. Exoplanet skies sketch a second branch of this map. Transmission spectra that first revealed water, carbon dioxide and sulfur dioxide now invite uniform surveys that measure the same bands across dozens of stars and planets, so that chemistry can be tied to stellar-type irradiation and metallicity, without the bias of isolated case studies. Phase curves at multiple wavelengths for the same world will assemble cross-sections of wind with height, clarifying where magnetic drag grips and where it lets go. Small worlds around quiet stars will receive denser campaigns that interleave visits across seasons, so that star spot evolution can be disentangled from planetary signals, and flat spectra can be tested for heavy atmospheres that hide behind clouds. Some rocky targets will remain out of reach for emitted light, but their lack of hydrogen-rich blankets will already focus future searches for secondary gases that trace volcanism or water loss. On sub-Neptunes, where hydrogen cyanide remains a tentative visitor, broader coverage at wavelengths where its bands recur will decide whether carbon-rich pathways truly dominate, while emission spectra will test whether the same molecules shape temperature inversions that change climate at depth. Weather forecasts for hot giants will leave the page and become movies. Eclipse mapping that currently sketches dayside spots will grow into sequences that watch vortices drift and belts sharpen, turning general circulation models into live hypotheses that must reproduce not only averages but also changes. Cloud microphysics will step from toy schemes into frameworks that allow grains to nucleate, grow, collide and evaporate in the same numerical world where winds race, so that mineral rain and rock clouds become outputs rather than inputs. Across all of these routes runs a common need time on target. Quiet shocks only harden when curves repeat, when lines recur at the same wavelengths with the same shapes, when maps made months apart show that structure persists or evolves in patterned ways. The telescope's stability and sensitivity make such persistence possible. Coordinated programs make it inevitable. The Nancy Grace Roman Space Telescope will add breadth with wide infrared surveys that find lenses in bulk and that establish the environment in which early galaxies live, while the extremely large telescope class on the ground will add sharpness with adaptive optics that split clumps even when no lens helps. Together they form a triangle with the James Webb Space Telescope at one corner, trading depth, width and resolution to close the loop between discovery and explanation. The open questions gather at the center of that triangle. How early did the first disks settle into ordered motion, and what fraction of their light comes from bursts versus smooth growth? How quickly did dust transform transparent gas into layered media that shape escape of ionizing light and seed complex molecules? How abundant are small halos without stars, and how do they steer the pace at which the bright tail rises? How large were the first black hole seeds, and did clump migration and weak bars feed them as soon as rotation appeared? What climates take shape when a planet's wind is leashed by magnetism at the top and runs free below, and how do clouds made of rock or metal alter heat flow? The map does not promise answers. It promises convergences where multiple lines of evidence cross. In those crossings, theories must commit to numbers. The James Webb Space Telescope will keep measuring until the space between anomaly and understanding narrows to a corridor of possibilities. The last surprise may be that the universe needs no new rules to produce its early strangeness. It may only need the same rules applied under pressure with fuel in abundance and time compressed. The script remains deliberately unfinished. The telescope has shown where to point the next stare, where to place the next slit, and where to expect the next silence that speaks. It leaves the sky holding its questions with poise, and invites the next seasons to read them aloud. Night gathers around the telescope, though in space there is only the steady dark that never ends, and the mirror holds it like a calm lake. What has been seen does not shout. It lingers as after-images of structure and chemistry and motion that arrived before comfort said they should. Galaxies small as sparks and bright as cities arrange themselves with a composure that suggests lessons learned quickly. Spectra leave deliberate gaps where lines should stand as if the universe edits its own sentences to make the reader lean closer. Dust appears like a hush, softening the light and speeding the work of cooling, while cold gas and warm cores sit side by side in a rhythm that feels both ancient and new. Gravity writes in curves that do not glow, yet the arcs they pull are precise, and in those arcs the quiet weight of the unseen is weighed. In tiny centres engines spin earlier than planned, and their warmth shapes the rooms where stars gather. Nearer to home, pillars and filaments turn out to be blueprints scaled to a pace the early universe prefers. Farther away, worlds eclipse and reappear, and their skies answer with molecules that bend light into gentle valleys and peaks. Winds whoosh faster than thought, clouds made of rock form and fade, and nights become laboratories for pieces of weather that would not last in daylight. All of it feels improbable only until it is measured twice then again. The telescope does not argue. It remembers. It keeps the faintest count, stacks the softest signals, and returns to the same places until the strangeness settles into shape. What remains at the edge is a held breath, that the first fires burned efficiently, that order grew inside tumult, that time was generous only with speed. The rest is a path, not a verdict, a set of lights far away that know we will come back.